Thanks, Douglas. Thanks for the. Oh, thank you. Thank you. Can everybody hear me fine? Okay, before I even start, who here is actually working on cryptography? Okay, that's way more than I anticipated. So I will probably run through the first few slides a bit because you already know all of this stuff. Yeah, first maybe I start a bit about myself. Douglas already introduced me. Just to give you a bit of a fuller picture, I studied, sorry, I'm a bit excited. So I studied pure math back in Germany, back in the days. And after studying that, I decided to do a pivot and switch to crypto, for which I moved to Bochum, which is still in Germany, and also a pretty nice city if you visit the right areas. And during that time, I spent a lot of time on the Fujisaki-Okamoto transformation Douglas already mentioned, which in particularly underlies the new standard for public key encryption, which we know as Kyber. Yeah, after that, I moved to the Netherlands to do a first postdoc, got lucky and got a permanent position there. And ever since I've been working still in this area of provable post-quantum security, but a bit more broadly. I also try to look at bigger protocols that are a bit more complex and harder to analyze. And I've also been looking just a tiny bit into quantum key distribution, which can be viewed as a key competitor with post-quantum cryptography. Okay, since you're all cryptographers, I will do away with this slide. We all know that crypto is important. And I guess we all also know that quantum computers pose a bit of a problem here, right? So who's familiar with Shor's algorithm? Good. Okay. So key point, all of our public key crypto can be viewed as being threatened by quantum computers. We see major developments in this area. So we are kind of worried, in particular because we all know of these store now, exploit later attacks where people just record everything that goes along the wire and then can break the public key crypto later and basically recover everything we communicated today, which isn't nice. So this is why there was this huge NIST competition to find better alternatives for public key encryption and for signatures. Okay, so just a few words about secret key crypto. The quantum impact here doesn't seem to be so bad to our understanding so far, but we still are stuck with the problem that we don't know how we could agree on symmetric keys without public key crypto, right? I mean, of course, we could resort to dragging them around in a big suitcase, but this doesn't scale very nicely if we just want to add our aunt into the family chat or something like that. Okay, so this I can also go quickly over. I think we're all familiar with public key encryption. The one thing I want to dig a bit deeper into, because I come from the area of provable security, is how we actually define security of public key encryption. So in crypto, we always think of this mean attacker, right? And what they could possibly do to threaten the data we are communicating. And for public key encryption, an obvious security goal, of course, is that if you don't have the secret key, such an encryption of a message that should remain confidential should be hard to invert. And another obvious goal probably is that encryption should not leak significant information about the plain texts that have been communicated. And this is a slightly stronger security requirement than the first one, right? There are schemes for which it's hard to recover a plain text from a ciphertext. Sorry, other way around. No, you know what I mean. So the two security notions are a bit different. And in provable security, we formalize these security definitions via security games. So here's the security game that formalizes that encryptions of plain text should be indistinguishable. So the adversary gets the public key, fixed to messages of its own choosing, and either gets an encryption of the first message or the second one, and then has to guess which game it's playing. Okay, and I guess you also know that the answer to the question, right? So raise your hand if this question has an obvious answer. Okay, since not everybody raised their hand, I will quickly give away the answer. So if we have an encryption scheme that is deterministic, and the adversary is allowed to pick its own 2 messages, and it gets a ciphertext and has to tell to which message the ciphertext belongs, then it can just compute the encryptions of the messages themselves, because encryptions are deterministic, so they always give the same result, and compare the 2 results to the challenge ciphertext it received. And one of those 2 ciphertexts he computed themselves will match the challenge ciphertext, so the adversary can easily tell in which game it is playing. So the answer is no. Deterministic encryption schemes cannot be NCPA secure, but they might still be hard to invert. Okay, and then there's also another kind of attack that you're probably all very familiar with, in which an attacker can just interact with an honest user and send around some kind of mangled ciphertext and see how the computer responds to that. Right, and if at first we maybe have thought that this is a completely theoretical attack that might not have a huge impact, in '98 we found out that this is actually not the case, and that attackers who are able to send nicely mangled ciphertext can use this to break the security of the scheme. And this is why we adapted our security notion. And yeah, now also consider adversaries for which we provide them with the opportunity to request decryption queries for any ciphertext they choose. Except maybe the provided encryption they got as the challenge, because if they ask the decapsulation or decryption oracle on this particular challenge ciphertext, they immediately get the answer to the game, right? Okay, so now we have talked a bit about public key encryption. So let's get back to what this has to do with sharing symmetric keys. So our goal will be to find a public key method to securely establish a symmetric key. And if you ask yourself, yeah, why wouldn't we just use public key encryption to send encrypted messages? The answer is that public key primitives are way more clumsy than symmetric encryption schemes. So it's much nicer to first establish an initial symmetric key via public key encryption and then resort to symmetric encryption. Okay, and a method that allows us to send over a symmetric key nicely is called key encapsulation mechanism. And this is exactly what the Fujisaki-Okamoto transformation will do. And this is also why NIST was not asking for public key encryption schemes that are post-quantum secure, but rather for key encapsulation mechanisms that are post-quantum secure. Okay, so here's just the syntax in case you're not familiar with that. So a key encapsulation mechanism looks pretty much like a public key encryption scheme. We still have a key generation algorithm that generates a public secret key pair. And instead of an encryption algorithm, we now have an encapsulation algorithm that just takes as input the public key and generates a symmetric key together with a ciphertext that you can view as an encryption of the symmetric key. And then as the counterpart to the decryption algorithm, we have a decapsulation algorithm that recreates the symmetric key from the ciphertext. Right, so Alice can send over the ciphertext and Bob can use his secret key to recover the symmetric key, and afterwards they can use whatever symmetric encryption scheme they like. Okay, and the security definition is also quite close to public key encryption. What we want is that a ciphertext shouldn't leak substantial information about the symmetric key. And the way we formalize it is again in a game-based manner. We have 2 games. The adversary has to distinguish. The adversary gets a public key, also gets a ciphertext that either belongs to exactly the symmetric key the ciphertext encapsulates, or a uniformly random key. And then it has to guess which game it's playing. And since we learned our lesson, we are now working with indistinguishability under chosen ciphertext attacks. So we also assume that the attacker can additionally request decryptions or decapsulations for any ciphertexts it chooses, except for the challenge, of course. So this additional chosen ciphertext oracle will be something we have to keep in mind later. Yes, Douglas already gave away in his introduction. The chems in the NIST standardization process all have, like if you look at it from a very high level, they all have the same approach. They first use some computational hardness assumption to generate a public key encryption scheme. This can be lattice-based, this can be code-based, or whatever. And then they apply to the encryption scheme a so-called public key encryption to key encapsulation mechanism recipe. So for example, Kyber is module LWE encryption plugged into FO. Frodo is based on LWE encryption, and then you plug it into FO. And for the rest of the talk, I will be talking about how this recipe looks, how we prove it secure, how it gets more complicated when we are considering quantum attackers, and how much time you can spend on improving the Fujisaki-Okamoto transformation. Okay, so who has seen the Fujisaki-Okamoto transformation? Raise your hand. Wow, okay. For the ones who didn't already see it, anyways, let's do a quick recap. So the initial idea is to start with a public key encryption scheme that is one-way secure, meaning ciphertexts are hard to invert, and then to use this to establish a symmetric key, right? So the idea I would start with is to pick some random message, to encrypt it and send over the encryption. And now the question is, how do we define the symmetric key we can establish with this method? So maybe a first idea is to set the symmetric key to the message itself. Does anyone see a problem with that? Mm-hmm. Sorry? No, it's even simpler. So if you really stick to the CCA security definition, we are now in a setting in which the attacker gets the ciphertext, so the encryption of M, and a key that is either uniformly random or exactly the message, right? So if, for example, the encryption scheme is deterministic, which we can't rule out generically, it would be super easy for the attacker to take the key, which is now just the message, to encrypt it and to see whether it ends up with the same ciphertext. So clearly this isn't secure. So what we do instead is to push the message through a hash function and to hope that the hash function behaves nicely enough such that it is super hard to get back from this result to the original message and hence compare it to the ciphertext. So this is the basic intuition. And if we think about whether this is secure, we usually do reductions. I will talk about this in just a sec. But the main goal is to show that the attacker now has zero chance at breaking the chem without inverting the encryption and thus contradicting our assumption that ciphertexts are hard to invert. Okay, so who's familiar with the provable security paradigm? Raise your hand. Okay, some, but not all. Okay, so the provable security paradigm in which I usually work, it rests on 3 pillars. So the first pillar is very obvious, a cryptographic design we want to prove secure. The second pillar is a security model in which we formalize what it actually means to be secure. Why do we give a formal, like in our example, this is just this security game for the chem, right? And why do we even do this? To avoid ambiguity, because something is secure can mean many different things, and this can lead to quite substantial misunderstandings and misuse of primitives that are placed in at a place where they shouldn't be. Okay, and the third pillar is a security proof. And all security proofs we do in public key crypto are based on some hardness assumptions. And the intuition of all of those proofs is always the same from a high level. It's always, if it's hard to solve some computational problem P, like in our case, inverting encryptions, then the design is secure. So in our example, this would be the Fujisaki-Okamoto cam resulting from this particular public key encryption scheme. Okay, and how do we prove it? So who's familiar with reductions? Raise your hand. Okay, also most, but not all. So the proof approach to do a reduction is that we imagine a black box attacker. So we don't know how the attacker behaves. We cannot make any assumptions about its choices of randomness, for example. And we assume that it breaks the design according to the security game we just formalized. Right? In our case, for example, it could be distinguishing the CAM output keys from random. And then we use this black box attacker as a subroutine to give an algorithm, which we call reduction. And the reduction uses the attacker to solve the underlying problem, which we assume to be hard to solve. And then we can reason, okay, if the problem is hard to solve, then such an attacker cannot exist. So this is glossing over a lot of details like parameter choices and asymptotic versus concrete reasoning, but this is the main intuition underlying reductions. Okay, and why do we even do this? My main point is that this allows us to really focus our cryptanalytical tasks on one particular problem. Like if you look at all of the designs that are flying around outside of this room in the real world, and if we look at very complex problems, it can be super hard to find a cryptographic attack or to reason about whether no such attack could possibly exist. If we have such a reduction, we know that it is sufficient to check whether the underlying problem will really be hard. Okay, so back to FO. The security proof for FO, as we've seen it so far, consists of showing that keys are hard to distinguish from random, assuming that ciphertexts are hard to invert. So we now do pattern matching. We imagine an attacker that is able to do such a distinguishing thing. And now we want to construct a reduction that uses this distinguisher to invert encryptions. And maybe at a first glance, it's not obvious to you how we can do this, because our attacker will just answer with, I'm playing the left game or I'm playing the right game. And also, we do not really know how the reduction could simulate the symmetric key if we are in the game where the symmetric key should actually match the ciphertext, right? So to deal with these two problems, oh yeah, here they are. So to deal with these two problems, we use the random oracle model. Who is familiar with that? Okay, so I'll be as quick as possible. In the random oracle model, we take a hash function and replace it with a very artificial object, which is an oracle box for a truly random function. And there has been some discussion about this. I will get into this later. But for now, let's just say that we now replace the hash function with such an oracle. So both the security game and the attacker must interact with this oracle box to get hash values. And let's see whether we can now solve these two problems I just sketched on the reduction slide. Yeah. So the first question was, how can we even simulate the symmetric key if we are in the game where the key should match the ciphertext? And now we can reason about how the key would be defined in the honest game. It would just be the hash value of the message, right? And since we now replaced the hash function with a random oracle, to which the attacker has to make explicit queries to learn anything about the outputs, we can argue that the attacker cannot distinguish this key like the hash value from a random value at all unless it makes such an explicit query. And our reasoning is then it must have somehow been able to invert the ciphertext, because otherwise it would not be able to post the respective query to the random oracle up to some tiny guessing bound. Okay, so this allows us to give a reduction that just replaces the symmetric key with random either way. And the attacker will only notice this later when posing the query, which we can then use as our output to the break the ciphertexts game. Okay, I already mentioned that some people have strong opinions on the random oracle model, and I completely understand them. So if we think about random oracle models, we have no theoretical justification because no hash function is perfectly random. We don't even know what it would mean to only be able to query a hash function as an oracle. And we also know of some counter examples, right? And there are some quite convoluted or artificial examples where we can prove the design secure in the random oracle model. But as soon as we instantiate the design with a concrete hash function, we lose this security guarantee. On the other hand, we have not seen any, so to speak, natural designs, no designs that weren't built exactly to make this separation come through, where we had a random oracle model proof and we found an attack. And at the very least, using a random oracle model proof will help us identify design bugs. So if you don't even get a proof in the random oracle model, there must be something wrong with your design, probably. And thinking about it on a bit higher level, if you have a generic design like the Fujisaki-Okamoto transform, so we don't make any assumptions about the public key encryption scheme, except that it is hard to invert, right? And if we find an attack on the design instantiated with a particular hash function, this also tells us that the attacker must have used some interplay between the hash function and the concrete public key encryption scheme at hand, no matter which public key encryption scheme we use. So this will also be kind of interesting in its own regard. Okay, so with this, I hope I appeased the people who are opposing the random oracle model, at least to some extent. Okay, so we've seen this initial idea. We just send over an encryption of a random message and hash it to get to the key. Oh, yes.
So those counterexamples typically make use of the fact that the random oracle doesn't have a polynomial description, whereas hash functions that are used to instantiate the encryption scheme do have polynomial descriptions. So my question is, do we have any counterexamples that separate the power of non-programmable because I think that those counterexamples show that there are some constructions that are secure relative to programmable random oracles, but there's no way to instantiate them with concrete hash functions. But do we have any separations between non-programmable versus programmable ones?
That's a good question. I don't know. So I guess this is more in the realm of TCC, and yeah, I don't know. I mean, distinguishing between programmable and just observable random oracles always makes sense, right? Yeah. Oh, okay. Yeah. Short answer, I don't know. Could be, but I don't know. Okay, so getting back to everything, so far we've seen an encryption scheme, a key encapsulation mechanism where we have that the keys are indistinguishable from random. But what we haven't seen so far is that these keys are still untouchable if we allow the attacker to request decapsulations for any ciphertext of their own choosing, right? So what we will do with our initial idea is to go with it and alter how the CAM encapsulates and decapsulates in a way such that our decapsulation algorithm will be able to detect dishonest ciphertexts and punish those by rejecting to respond with a useful key. So how do we do this? What we will do now is to switch up our encryption scheme in a way that might look weird to the cryptographers in the room at first, because we will now make the encryption algorithm deterministic by using as the encryption randomness the hash result of the message under a different hash function. Or you could also imagine the same hash function, but with a domain separator or something like that. But for simplicity, let's just assume that this is an independent hash function. Okay, so the encryption randomness is now immediately tied to the message. And to decrypt, we will now do something that people who have been working a lot on FO are calling a re-encryption check. So after decrypting the message, we will re-encrypt the message and check whether we actually end up with the same ciphertext we received. And only if this happens, we will actually respond with a proper symmetric key, and otherwise we will reject. And why is this a nice way to mitigate chosen ciphertext attacks? So assuming that it is really hard to land on a proper encryption by random guessing, so assuming that the encryption scheme has high entropy, it's really hard for the attacker to come up with ciphertexts that will faithfully decrypt to a message and re-encrypt to themselves without querying the hash function on the message to get the proper randomness that was used to create the ciphertext if it is a valid ciphertext. Okay, but if the attacker has to use its own message, query the random oracle to get the proper randomness, and then encrypt this thing to a ciphertext, and then get the symmetric key, then the attacker could have come up with the key in the first place, right? Because they can just compute the hash function, the key generating hash function applied to this message themselves. So by this, with this trick, we have basically made the CCA oracle useless to the attacker. Okay, on the other hand, I want to mention that this re-encryption check has its drawbacks and limitations in practice because it opens up venues for side channel vulnerabilities, because this step involves too many dependencies on secret and public key. And actually, if you can use a side channel device, this allows you some leakage to get some information about the secret key. So this isn't nice. And the question why we still do it is that we don't have any smarter approaches so far. Okay, and another thing I kind of glossed over so far is what it even means to reject. There are two main venues to reject invalid or dishonest ciphertexts. First option is to return an explicit failure symbol like bottom. Second option would be to return a pseudo-random key. So there has been some discussion about which method works best. If we look at the NIST candidates, they all use this return a pseudo-random key and thereby kind of hide the failure approach. I think the main reason probably is because at the point at which these design decisions were made was that we had quantum proofs for the approach that returns the pseudo-random key, whereas quantum proofs for versions that return explicit failure symbols at that point had been elusive. But that's just my hot take. Douglas might have a different opinion. But to me, it's kind of weird. So people always say, like, if you return a pseudo-random key, you basically hide away that a decryption failure or something else occurred that shouldn't have happened, right? But if we think about how we use these CAMs, usually we use them in bigger protocols. that will fail to communicate with each other anyways if we use a pseudo-random key. And at the latest, at this point, we will notice that something went wrong. So returning a pseudo-random key, in my view, doesn't really hide away that something went wrong. Okay, so end of my hot take. Who of you is familiar with post-quantum security and how we reason about security when we are considering quantum attackers? Okay, not so many. How many of you had a lecture on quantum computation? Okay, that's a bit more. Okay, so I will try to say a bit about the basics, but not too much so I don't bore you. So if we are thinking about quantum computers, we start by thinking about quantum bits. And maybe you've heard this phrase that quantum bits are a bit of 0 and a bit of 1 at the same time, right? So what does this mean? What this means, if we just, so let's not think about the physics because I'm not a physicist. Let's just think about how we model quantum bits for quantum information theory. So we have two base states, 0 and 1, but we also allow linear combinations of those. So what we allow is linear combination where the two scalars or coefficients can be viewed as probability amplitudes, basically. So what we also require is that if we norm them and add them up, that we end up with 1. And this is what we call a superposition of the two base states. And hopefully easy to understand example is the half-half state. So since we want them to be normalized, we also have to take the square root of the twos. But we see that both 0 and 1 appear with the same amplitude, or as we soon see, with the same probability. Okay, what we also can do with quantum bits is to measure them, which allows us to extract classical bits from these quantum linear combinations. So we have a quantum bit, we shove it through a measuring device, and in the end, we will end up with either 0 or 1. And if we are just thinking of the measurement that we are usually thinking of in cryptography, which is called the computational measurement, what happens is that this linear combination collapses to 0, exactly with the probability indicated by the first scalar, and 1 with the probability indicated by the second scalar. Okay, and if we now want to generalize this to arbitrary length bit strings, we basically do the same thing. So we make a very long linear combination of all potential base states. So here's the example for bit strings of length 2, but you can easily generalize this to an arbitrary length. And we have this similar requirement that if we norm all of the scalars and add them up, then we want to end up with 1 because we will want to treat them as probability distributions. Okay, and we can also compute on quantum states, and the fact of life, as I understand it, is that any quantum computation can be described by a linear mapping that is nicely invertible in a certain way. And as an example, let's look at this map that is described by this table. So here are all 4 potential input values. If we start with 2 bits, since this thing must be nicely invertible, we will have output of the same length. And this describes the mapping that just XORs the second bit, the first bit into the second register, right? And we also might know this as the C0 gate. And we have to apply something quite similar to random oracles. So how can we describe them in a nicely invertible way? So remember that we wanted to treat our random oracle as an oracle box to which the attacker has access. And what we do now is, so say we have a random oracle that goes from some input set X to some output set Y. Then we define this box onto registers that represent the input register and output register. And what we do is just that we XOR the function value on the particular base stage into the second register. So if we set the output register to 0, we exactly get the oracle value of X in the second register. And these are only base states, of course. And we have to think about linear combinations, right? Because we want to think of quantum bit strings. So what we make OF do is to simply carry over the probability coefficients or amplitudes. Okay, are there any questions concerning this? Okay. So if you have questions later, you can of course also come and talk to me. So to get a better understanding of how quantum random oracles complicate our proofs, we'll now revisit the security proof for the Fujisaki-Okamoto transformation that we had just seen, where we argued that we can do a reduction because we can essentially see the plaintext that belongs to the ciphertext in the attacker's queries to the random oracle, right? Now, the tricky part about the quantum random oracle is that the attacker will now pose superposition queries. Meaning if we are thinking about this particular message, it will be hidden in a larger superposition. So it's just one of the base states. Might be that there are many others. So how could we even extract the message we care about, the solution to our break the ciphertext game, from the queries? An initial idea might be that we could just measure the queries that the attacker is making to get classical states, right? But this would also mean that we change the query because it collapses. And we would have to convince ourselves of the fact that this does not derail the attacker's behavior too much. Like if the attacker is asking for something and we are changing the something for which the attacker is asking and then respond, it might look weird to the attacker, right? Okay, but luckily there has been quite a lot of work on how we can generalize this random oracle model approach to the quantum random oracle model. And the main takeaway is that even if the attacker does superposition queries, this measuring will not change his view too much unless he queried the message with a very, very high amplitude, which would allow us to extract the message. So unfortunately, so far, these tools that we use to replace our classical random oracle model reasoning with quantum so far are quite loose in the security parameters. And we don't yet know how tight we can get. So in consequence, the proofs so far only apply to less efficient schemes, right? Because we have to scale up the parameters to make up for the reduction loss. Okay, but at least there is something there and we are working towards getting the bound as tight as possible. Yeah, and another thing I hid away so far in the context of post-quantum encryption is that many post-quantum schemes exhibit decryption failures. Who has heard of decryption failures and their importance? Okay. So if we think about group-based encryption or prime factorization-based encryption, if we encrypt a message and then decrypt it, we always end up with the same message we started with. And for example, for lattice-based schemes, this is not necessarily the case. We do some modular operations, and it might be that we have some modular wraparound while we are doing the computations. So we end up with a different message than we would have expected. And intuitively, you could think that this will happen with a very small probability, so we might be able to dismiss this. But since we are now dealing with chosen ciphertext security, so with an attacker that can choose whatever ciphertext they like, it's really possible that they try to search for ciphertexts that are particularly easy to fail. Right, so this average case probability doesn't help us with our security reasoning because the attacker could just be mean. And it has been observed previously that failures are secret key dependent, and this actually opens up an attack surface. So there has been some work on how we can exploit failing ciphertexts to learn enough about the secret key to break the KEM. And what we did originally was to just assume a worst case bound, which we called delta correctness back then, on the failure probability, so that we make it hard for the attacker to find failing ciphertexts in the first place. This is a bit of a sledgehammer argument, right? And there are also some facts that I found irritating when we had finished with this paper. So the first irritating fact was that when we were working in the quantum random oracle model, the result we obtained gave a Grover-like search bound. So it really represented a quantum search. And if we think about it, quantum search usually involves that you are able to compute the predicate and superposition. But here in our example, asking the decapsulation algorithm, which will give you the information whether the predicate is satisfied that decryption fails, can only be asked classically. So this bound is somewhat dissatisfying. And another thing I found kind of irritating was that this bound is somewhat unnatural, and I will talk about this more in the next slide. So these were the irritating things, and then there was a problematic thing, namely that the way we estimate this bound does not match nicely with our security proofs. And I will encompass all of this in more detail on this slide. So if we think about this worst case correctness bound that I just described, you can imagine this as the success probability in a particular game in which the attacker gets the public key and the secret key, and they have to come up with a message such that encrypting and decrypting will not yield the same message, right? And the irritating thing here is that if we think about NCCA security of the KEM, the attacker will never get to see the secret key. So we wonder, why is this even necessary to provide the attacker with a secret key? This looks artificial. And a second more important thing is the way that scheme designers actually estimate the success probability makes the assumption when they are estimating and doing some calculations that the attacker does not have the secret key. So we have a mismatch between what we require in our security proof and what people actually show when they are estimating the bound. And this was only caught by a colleague while he was working on formal verification of the security proof of Kyber. And it took quite a while to actually notice this mismatch, which might be a bit surprising by now because it looks kind of obvious and when you write it like that, right? Okay, so what a few colleagues of myself and I did was to give a more thorough treatment of decryption failures. So we showed that we can also do the CCA reasoning if we assume a correctness bound that does away with the secret key, which feels more natural and more satisfying, and also makes the security reasoning compatible with what people have done in practice when they estimated the bounds. Another advantage I find I want to mention right away was that the technique that we did in the paper was completely agnostic to how we deal with dishonest ciphertexts. So we don't care in our paper about whether we return an explicit failure symbol or an implicit key. So the main advantage of this result is that it aligns the two previous unaligned rejection methods in terms of quantum random oracle model security bound. and just to do a very brief sketch of what we did there was in the classical ROM, it's pretty straightforward to show that any helpful decryption query will immediately translate to the adversary having found a failing plaintext without knowing the secret key. And then you can dissect this success probability a bit further to get a more fine-grained analysis and to get sharper bounds. But we also care about quantum, right? So we had to translate this into quantum. The first step can be done with one of the more sophisticated approaches to the quantum random oracle model that we've seen in recent years. It's called extractable quantum random oracle model, and it allows almost classical reasoning. So this is a really convenient tool once you understood how to read it. For the second part, for the more fine-grained analysis, we did some quantum search bounds. And the last thing that was left to do was to give this everything looks random until there was a problematic query to this more sophisticated quantum random oracle model. Okay, yeah, something that people brought up then as a response was that this, due to this more fine-grained approach to correctness errors, this poses new analysis tasks on the designer if they want to get sharper bounds. And they also reasoned that designers might be fine with this heuristic, like just assuming that it doesn't make too much of a difference in the bounds if an attacker would get the secret key or not. So what I did recently was to take the advantage of the paper I just sketched, so this realigning of the two rejection variants, but to reconcile it with the original approach to correctness errors. Okay. Yeah, one of the last things I wanted to mention, I already mentioned that I can talk about FO a lot, and you can also spend a lot of time on it. And one of the things that we noticed was, as you already heard, it's not great if attackers can trigger decryption failures, right? And for lattice-based schemes, you have encryption where you basically add the message. So the message does not influence the decryption failure too much. For entry-based schemes, you do a multiplication, and there it's a bit easier to reason about. So it's easier to reason that attackers might get leverage from picking particularly bad messages. And what you could do would be to increase the modulus, but then you would have to increase a lot of parameters to get a scheme that matches what you need. So what we did for entry-based schemes was to create some pre-transformations that kind of make it hard again to find failing plain texts that are worse than others. Okay, and I think this is even the last thing I wanted to mention. What we haven't thought about so far is that in practice, the CAMs will be used mostly everywhere. So we'll have a lot of different users who are using this algorithm, and they will be exchanging a lot of ciphertexts. And one of the things we would like to see in practice is that if we collect a lot of information about Alice, this shouldn't help us with attacking Bob or Carol or whomever. So the main idea to resolve this is to bind the CAM's behavior to a particular user by including a prefix of their public key into the hash functions. So the encryption randomness is now tied to the prefix, and so is the symmetric key. And since we are in a world where we assume the hash functions to be random oracles, this makes the two worlds for Alice and for Carol completely independent of each other. Okay, and I think this is it. And I'm happy to take any questions.
look at a slide about decryption errors in lattice-based schemes.
In lattice-based schemes.
So you had a slide where you said that lattice-based CPA secure encryption schemes come. Yes, this one. So I think that the main issue there is that you might have CPA secure encryption schemes where malformed ciphertexts, meaning that ciphertexts that are not in the support of the encryption algorithm, will decrypt differently with respect to different secret keys. So what I'm saying is that it is easy for most lattice-based schemes like regex to make it perfectly correct if the ciphertext is honestly generated, meaning that if the ciphertext is actually an output of the encryption function. So if you think about the regex scheme, the way that it's presented, it has a negligible decryption error even for honestly generated ciphertexts. But there is a simple trick in order to make it perfectly correct, like to make it perfectly correct for most of the public keys.
But then you would scale up the modulus, right?
I don't think so, because what you can do is that essentially what I'm saying is that you can trade correctness for security. If you think about the regex scheme, let's say that the decryption error is epsilon. So I can tweak the regex scheme so that it's perfectly correct, but it is secure, but its security bound will degrade by epsilon. So you can kind of trade correctness for security. But the main challenge is that even though it is perfectly correct for honestly generated ciphertexts, but for malformed ciphertexts, you can have a situation where, let's say that you have a public key and there are two different secret keys for that public key. I might be able to produce a malformed ciphertext that decrypts differently under those two different secret keys. So if I keep making decryption queries like this, I will learn more information about your secret key. I think that's this is going to be a challenge.
So what you're saying is that you can just like start with a message. Oh no, you start with the ciphertext that's not even in the range, and then you kind of like mangle it around until you hit the sweet spot that basically gives you information about the secret key, right? I don't think I said anything about correctness errors for lattice-based schemes on that slide. I think you are referring to what I said when we were talking about entry, right?
So I'm talking about bullet. I'm talking about line 2, where it says that with some small probability, it might happen that if you encrypt him, so encrypting him meaning that encrypting him honestly by following the protocol, and then decrypting it with a secret key might not return in. What I'm saying is that yes, so the way that regex is presented, it satisfies that property, but there's a very easy way to tweak regex so that it will be perfectly correct for honestly generated ciphertexts.
Got it. So I think the main reason why I didn't even mention this is because we already made the decapsulation algorithm reject whenever a ciphertext is not hit by the encryption of the decryption, right? And if we start with a ciphertext that is not even in the range of the encryption algorithm or the support, as you said, then we will always end up in the rejection branch because no such message could even exist. So we kind of forcefully excluded this attack in the first place. Yes. Sorry? Yes. I can say it's hard. So finding an So by now we've seen some kinds of other sanity checks on the ciphertexts, but completely getting around any kind of sanity check seems unfeasible to me so far, but this is the paper in the writing, so it's the rework. So for example, if we think about something like McAleese, and are you familiar with that? McAleese, it's about, so if we think about that, the messages and the randomnesses, if they are picked honestly, they adhere to a pretty strict format. So if you decrypt, you can also check whether the message adheres to this format. And then you can also, because messages and randomness are immediately bound to each other by this hypertext, you can also do a sanity check on the randomness. And then you can say if they don't adhere to the format, there must be something wrong. But does this really circumvent side channel attacks? I'm not yet sure. So we haven't seen any as far as I know. Doesn't mean that we won't see any in the future, because we are still behaving differently depending on what we did with our secret key and the result, right?
So far, it's like it's tied, like it's specific to this. It's not generic.
Yeah, that would be nice if we had something that works generically, but so far this has been elusive. Okay, anything else? Okay. Thank you.